So we will start about 4 p.m.
Yep.
So more people is jump in. You can see the second attendees, like the numbers go up. So
yeah.
we have the 300 registration, and probably we have to wait about another 2 minutes. Welcome. So we just wait another 2 minutes for probably for 2 can start, because I have about 2 minutes introduction, and the presenter is the introduction. Yeah. Gonna start about 4 minutes. Right now, our attendees are probably like 54. Okay. Okay. I'm gonna start the webinar because every presenter they probably have 25 minutes presentation. So let me start this webinar session. Okay. Hello everyone. I'm Simon. I'm the graduate GIS specialist in data analysis. Currently also is a Cashier Academy in the USW Sydney. Great to have this chance to represent the GIS and digital analytics group and the young professional community in the GCA to host this webinar. Through the popular trends of artificial intelligence in geospatial data, GCA want to set up series of AI webinars related to geospatial data. This one will be the first one to have the introduction between the smart infrastructure and the geospatial world. So first thing first, we acknowledge the Aboriginal and Torres Strait Island people and traditional owners, and the continuing connection of indigenous people as the traditional custodian of this land, and pay our respects to the elder past, present, and emerging people. The webinar agenda, we will divide it 4 parts. First part is introduction about our presenters and specific summary about the presentation. And the second part is a presentation by Bing. Third part is by Miles. So the final part, we will have a Q&A. You guys can text your question when our presentation goes through, and I will highlight that and read that and let our presenters answer that. So we're excited to have this opportunity to invite these 2 presenters to talk their vision and experience in this webinar. For our first presenter, Dr. Bin Liang is a senior lecturer in the UTS Data Science Institute. Dr. Bing is a visionary data scientist at the forefront of data analytics machine learning, and computer vision. As a senior lecturer, he is generating innovative solutions to complex challenges facing industry and society. He's focusing on the impactful industry collaboration and applying the deep learning for earth science advancement. Today, Bing's presentation will offer a compelling introduction to the convergence of AI, infrastructure, and geospatial technology, with a particular focus on the applications in water utilities and remote sensing. And attendees will gain insights into how AI is shaping the smart infrastructure management and predictive maintenance. Bing will dive into the geospatial domain, emphasizing the transformative role of deep learning and generative AI in enhancing object detection and segmentation for a more efficient and sustainable future. So right now, I'm going to hand over to Bin Liang. I will stop sharing. Dr. Bing.
Yeah. Thank you, Simon. I'll share my screen. Oh, yeah. Thank you, Simon, for the organization of this webinar and the introduction. So yeah, just yeah. Hello to everyone. Welcome to this webinar about the AI in smart infrastructure and the geospatial world. It's my pleasure to be here to share my experience and the thoughts about this exciting and rapidly evolving topic. As we know, AI is a hot topic in these days, drawing the attention from the professionals from different fields. The excitement is from the diverse applications that AI offers, revolutionizing the industries and solving complex problems. So let's start with this one fascinating application of AI, which is image generation. Take a look at this picture. It was generated by DALL-E using just the specific prompts here: AI in smart infrastructure and a geospatial world, and give me a digital art. So we can see that there are some elements in this picture related to instrument and infrastructure and the geospatial items, so which is amazing. So now let's dive into the field of AI, where many technical terms such as ChatGPT, deep learning, machine learning, and AI stuff may seem like a maze of confusion. Understanding the differences among these terms is crucial as you embark on your AI journey. So understanding the distinctions between these terms can give you a clearer picture of how AI has evolved and its history, and also how AI progressed over the time. The evolution of AI is a progression fueled by the transformative power of big data. AI served as the foundation, leveraging data for intelligent decision making. Machine learning steps into the spotlight, utilizing big data to enhance learning from diverse experiences. And then deep learning takes the center stage, employing neural networks and thriving on extensive data sets for complicated tasks. Then is the ChatGPT, which is the advanced large language model that stands as a testament of AI in this field. So especially for ChatGPT employs the deep learning architecture, which is the transformer, which is very powerful. So we can see the AI serves as the overarching umbrella term covering the various topics and the methodologies in this area. And also this chart can give you a good view of overall picture of how AI involves with the big data and what's the relationship of these technical terms. Moving on to the topic of AI in smart infrastructure, let's explore a successful application within the water utility sector, using it as a compelling case study to present the key elements and components in this domain. So this is my first part of the AI in smart infrastructure. So our research center, the Data Science Institute at UTS, has been at the forefront of collaborating with water utilities nationally and internationally to tackle the real-world business challenges, which is listed here. So these challenges prevalent not only in water utilities, but also across various infrastructure sectors. So I just use the water utility as an example. We can see there are several challenges listed here, like the aging infrastructure, growing population, limited expenditure, and service interruption. The foundation of this successful solution is data, as we can see, as we already seen that the big data is the foundation of AI. So diving into the specific the data we've utilized, there are four key sources. The first one is the attributes of the assets. This includes the details like or attributes like the assets of material or the age of the assets. And the second one is operational or IoT data, includes the parameters such as pressure or readings from IoT sensors or devices. And third one is the environmental geospatial data. This can include the weather conditions or and soil information. Last but not least is the historical records, because we need to learn and discover the patterns from the historical events. By feeding these diverse data sources into the model, the patterns can uncover and learned. So this leads to the development of predictive maintenance strategies, offering a proactive approach to address the potential issues before they escalate. Just give you two pictures here. This two pictures provide a glimpse into two distinct maintenance approaches in smart infrastructure, preventative and reactive. On the right-hand side, this is the traditional approach, which is the reactive maintenance. This strategy involves responding to issues as they arise. It's more like a fix it when it's broken strategy. And on the other hand, the left one is the preventative. So through the application of AI, our objective is to revolutionize the conventional reactive maintenance model, transitioning it into a preventative maintenance strategy. So the utilization of AI empowers us to not only respond quickly, but also to foresee the potential issues, therefore optimizing the overall performance and the reliability in the system. So now let's look at what the data looks like. This is just an example of the data we used. So in this picture or in this image, the lines represent the water pipes, while the dots mark the historical failure event, and the regions are distinguished by various colors indicating the different soil types. So furthermore, the diverse colors of the lines highlight the distinct types of assets and the corresponding failure records. This snapshot helps to comprehend the complex relationship between the various elements in this task. As discussed earlier, our model has incorporated over 20 factors or features from a variety of data sources. However, in navigating the complexity of this task, we've already seen in that picture, we encounter additional challenges beyond the integration of multi-source data, which are listed here. The first one is the diverse failure patterns. The occurrence of failures is not uniform, but rather follows distinct patterns. So this requires a robust approach. And the second one is the sparse and imbalanced failure data. The data set presents instances where the failure events are not evenly distributed. This poses a challenge in training the model effectively. And also the third one is that sometimes the data sets could be incomplete or could be noisy. This also introduces an element of uncertainty, which requires a strategic handling to ensure the robust prediction. And lastly, we confront the challenge of long-term prediction. Anticipating the failures over an extended time frame requires us to address the temporal dynamics. So we need the incorporate the temporal information to make the predict task more complicated. So as we navigate the complexity of this task, it's not just about the quantity of data, but also about the comprehending different patterns, addressing the data imbalances, handling the data incompleteness, and extending to the longer term of the prediction or modeling. Now let's take a look at this framework of our water main failure prediction. from the data to the outcome. As we follow the data flow, the integration of multi-source data serves as the foundation for our predictive model. With this process, we introduce a pivotal component, which is the feature engineering. So this key function or key component involves the extraction and the discovery of valuable information from the raw data from this multiple data sources. Got it. So the feature engineering usually we need the guidance from the expert from the experience and the domain knowledge from the expert. And it's worth noting that traditionally, this feature engineering step is a manual process. So this is different from the automated approach commonly seen in the deep learning. A topic which is a topic I will cover later. Now moving forward, these carefully crafted features become the input for our machine learning models, and specifically we employ the ensemble learning for its robustness. Ensemble learning performs better at the handling challenges, like I mentioned earlier, like incomplete data sets and also the imbalanced data set, incomplete data set and imbalanced data set. So the outcomes are twofold. First is we generate a priority list. This is a compilation of pipes or assets ranked by the predict failure probability. And also this list can serve as a proactive tool for target maintenance efforts. And the second one, we extract the feature importance. This is the key aspect in interpreting the results, because people always say machine learning is a black box. We don't know the details and how that works, but we can use this feature importance to interpret, to understand why this model works and how the model works to tackle this different kinds of data sources or features. So in summary, this is the straightforward yet effective framework leveraging the multi-source data, strategic feature engineering, and robust ensemble learning to provide the actionable insights and enhance our understanding in this of this problem. Yeah, this slide shows the results of the solution. With the priority list, we can visualize the risky pipes in the map because we have the probability for individual pipes. So this map shows an example of the top ranked pipes, which is colored with colored representing different risk levels. And also, in order to evaluate the model, we have compared the prediction results with actual ground truth data by calculating the percentage of detected failures, which is the y-axis, along within the inspection rate, which is the horizontal x-axis. So this is the in this figure we can see that more than 50% of failures can be detected within this top 10% inspection rate. So these results demonstrate that the model is capable to provide valuable assistance to forecast and plan water main renewals with more confidence. Furthermore, based on the feature importance from the developer model, the key features can be identified, which is shown here. So you can see that the top ranked features are the length and the size, which is aligned with the domain knowledge. To conclude this part, here's some takeaways for you. The first one is the data integration for holistic insight. So first and foremost, we emphasize the critical importance of data integration. By merging diverse data sets from multiple sources, we are aiming to have a comprehensive view of the problem. This holistic insight can give us a foundation for informed decision making and predictive modeling. And the second one is the integration of domain knowledge. Alongside the data, we underscored the value of integrating domain knowledge. It's not just about the numbers. Understanding the complexity of the industry adds the depth to our analysis and ensure the model align with the real world scenarios. And also the feature engineering can enhance the models. And last one is the predictive maintenance and risk mitigation, because this is our ultimate goal to achieve this. So armed with the holistic insight, integration of domain knowledge, and the well-crafted features, we are not only responding to the issues, but predicting and preventing them. This proactive approach ensures the long-term use and efficiency of our solution. So to conclude, these takeaways can give you a high level of how AI can be used in the smart infrastructure. Now let's move on to the second part, which is the AI in the geospatial world. We've already witnessed the powerful applications of AI in the geospatial area. I would like to dive deeper into some interesting topics in this area, and I'll introduce some interesting and useful and popular AI tools and methods, especially for the classification problem and segmentation problem. So, for instance, consider the task of land cover classification using the satellite imagery. AI algorithm can analyze a huge amount of data and accurately categorize different land types. The results can be used for the urban planning, environmental monitoring, and agricultural management. Additionally, in the area of segmentation, the AI plays a crucial role in capturing the boundary of the objects within remote sensing data. A noteworthy example is the identification or detection of objects in aerial image for disaster response. So it becomes evident that AI not only enhances our capabilities in geospatial analysis, but also open up new opportunities and possibilities for addressing real-world challenges. For classification task, I would like to start with the traditional image classification. So my research background is the computer vision, and I know how the AI involves in the image classification problem. The traditional image classification techniques heavily rely on handcrafted features. For example, the hard features or silk features and other handcrafted features. These methods have paved the way of AI, but they do have certain limitations, which are listed here. The first one is the limited representational power. The handcrafted features may not fully embrace the richness of complex patterns and variations in the data, so they might fail in capturing the complicated structures and the textures that make the visual world so diverse. And the second one is the sensitivity in the image variations. The traditional methods can sometimes be like, delicate instruments, and they demand the complicated tuning, and also they are sensitive to changes in lighting, scale, rotation, or viewpoint. So this we need to keep in mind when we use the handcrafted features. They may work in one scenario, but they may not work in another scenario. So we need to test the features in different scenarios. So the third one is the manual feature engineering. The crafting effective features become a manual expedition, relying on domain knowledge sometimes and complicated engineering. So this is a time-consuming process. And also the fourth one is the lack of adaptability, which I mentioned already. So to tackle this, address this limitation, and with the large volume of data, we have the deep learning methods. So having discussed earlier the limitation, now this is the cutting edge advancement of deep learning. Unlike the traditional methods relying on manually engineered features or crafted features, deep learning empowers machines to automatically learn the complicated representations directly from the data. For example, deep learning can capture the complex patterns and variations by automatically learning the features, and also it is invariant to and robust to the variations in lighting, scale, rotation of different viewpoints. So this can give us the this can give us a more flexibility and adaptability of the model. So I'm showing you and giving you an example here. So addressing the complexities of environmental monitoring, the identification of land cover and the land use is a very challenging. So this complicated data set often involves the field surveys or the analysis of satellite image, which is the process known as the remote sensing. So in this example, I use the data set, use the data set and also deep learning to have a accurate classification model. In this data set, it has 24,000 images across 9 distinct land use types. So you can see some sample images here, and the distribution of the samples in this 9 classes or 9 categories are shown here. So you can see it's quite a huge amount of data. Different from the traditional image data like RGB information, the remote sensing images can have more channels encoding more information. So this remote sensing data or images are from the Sentinel-2. Each remote sensing image is a mosaic of 13 bands, which listed in this table. So different bands, they capture the diverse information from different perspectives. It's crucial to note that these bands come with different resolutions, and also promising the need for a thoughtful normalization when you employ multiple bands in the analysis. To navigate this complex data landscape, we've used the power of popular deep learning classification architecture, which is the ResNet 50. And so this specific framework is adapted to at handling the nuances inherent in remote sensing tasks. And this model is known for its depth and efficiency, making it particularly suited for this task. Moving on to the experimental phase, my curiosity is to investigate the impact of utilizing different bands of the classification and on the classification performance. To explore this, I conducted the experiment with the 4 distinct settings here. The first one is the 13 bands. So all the 13 bands are used to fit into the model. And also the second one is just use the RGB information, RGB bands. And the third setting is use the high resolution bands. And the fourth one is the special bands, which incorporates the domain knowledge in remote sensing. So let's look at this example. We can see that the comparison results shown here, the special bands or the combination of the 4 settings give us the best accuracy. In contrast, the other 3 settings yield the accuracy ranging from 80% to 85%. So this results of us two noteworthy insights. The first one, more data doesn't guarantee better performance. So the settings with all 13 bands, while comprehensive, doesn't necessarily outperform more targeted band selections. And the second one, domain knowledge, holds the significance. Despite the powerful capabilities of deep learning in automatically learning features, the influence of domain knowledge still remains paramount. So in this context, the settings with the special bands combination showcases its importance of the domain experts. I'll just quickly go through. I'll just skip the results and to the segmentation part. So for the image segmentation, there are also the traditional part and also the advanced part. So the traditional approaches also involve the applications of use the thresholding and also the clustering to give you the boundary or the part of the image. And also for the advanced parts, also deep learning is a key one. And usually in deep learning, the popular architecture is the UNet. So there are several key components in the UNet. the encoder-decoder structure. This feature can give us the model to grasp the both global and local features effectively, and also the skip connection here. It's like the connection link corresponding layers between the encoder and the decoder. This can preserve the high resolution information during the downsampling process and facilitate the accurate segmentation. Originally, this architecture was designed for biomedical image, but currently it has been extended into other fields like remote sensing or satellite imagery for the segmentation. There are several functions and settings we can use in the segmentation, like cross-entropy loss, focal loss, and IOU loss. It's like the parameters or the settings you need to tune when you apply your algorithm into specific tasks. So here I use the different loss functions and to see how that performs for the segmentation. So in this scenario, we can see this original image data and this ground truth, and this is the segmentation results using different loss functions. So you can see that different loss functions, the unit with different loss functions can give you the different results, and that highlights the selection of the specific loss function is very important. Usually, the cross entropy loss can give us the results in the can give us the better results in the large elements or items, and the focal loss function can give us the detailed segmentation. Last one, I would like quickly share the emerging model, which is a meta segment anything model. So yeah, this model was originally generated and proposed for segment the traditional or the pictures or the images, but we can some researchers already to extend this model into other areas like remote sensing area. So here to just share with you two valuable tools or resources, which if you are interested, you can take the details of the links here. So on the left-hand side, you can see a tool which allows for the interactive segmentation. So you can, with just a few clicks, to identify the foreground and the background, and the model can quickly provide an accurate boundary. And the right-hand side tools can leverage the text prompt for the segmentation. You can input the free text description like tree or the swimming pool, and then the STEM model can give you the results of the segmentation. But just keep in mind, this is the foundation model which is not tuned or refined on your specific task. So if you apply this model into your specific task, you need to get the better results, you need to refine it and fine tune this model. And another resource is there's a packaging ArcGIS which is built on top of SAM model, and you can see the results here. So yeah, takeaways for this part. Yeah, so the first one, the geospatial data fusion. When you have the data, especially in geospatial area, you need to think of how to combine them and which combination of them is more useful in your valuable for your specific task. And the second one is we've already seen the AI advancements in the land use and cover classification, and also for the semantic segmentation task, we have shown you the unit and advanced the SAM model, which can be extended into this field. That's the vision. Another one is the vision foundation model. So vision foundation model is the example. A good example is the SAM model. So in summary, that's the intersection of AI and the geospatial world is transforming how we perceive and analyze and understand our environment. And hopefully this takeaways can signify not only advancements in technology, but also the potential of a more suitable and informed approach to managing and understanding our planet. Yeah, that's my part. Over back to you, Simon. Thank you.
So right now, I'm gonna to introduce the second presenter, and it's Miles. And give me a second. Miles currently is a senior geospatial engineer working in the Transport for New South Wales, previously serving as a senior developer in the S3 Australia. He is also for the IRM certified embed AI and IoT engineer, and FME certified professional owns the patent of augmented reality in Australia. His decades-long career impasses the extensive experience and knowledge in the GIS data analysis and data analytics, as well as GIS software development, keen on innovation and sharing knowledge. Mass presentation will guide us through the popular AI categories and methodologies such as the GPT and neural networks and reinforcement learning, shedding light on the seamless integration in the GIS. During this session, Miles will first introduce the AI foundation, followed by live case demonstration of GeoAI. And this real-world example will showcase how the AI can be effectively harnessed in the GIS application. You can expect to gain the valuable insights and ideas on how AI can enhance the GIS works on and projects. Okay, right now hand over to Miles. I'll stop sharing.
Okay, now I'm sharing my screen.
Yep.
So can you see me, Simon?
Yeah, sure. I can see your screen.
Yeah, cool. So yeah, let's get started. So hello everyone, my name is Miles, and today my presentation is the introductions to the GeoAI. So we all know that AI has lots of categories, and generally speaking, it can be divided into two types, the supervised learning and the unsupervised learning. And in the supervised, we got, for example, the regression, the neural network, the SVM, and some mathematics methods like probabilistic algorithms like GIS, and some tree type algorithms like decision tree or random forest. And there are a lot more right there. Yeah, I just put a dot. Yeah, okay. So another type is the unsupervised one. We got, for example, the clustering, like the very popular ArcGIS Pro or ArcMap toolbox, like a density clustering and nearby finding, that kinds of tools. The root algorithms are based on the unsupervised learning. And we got the RI, reinforcement learning, and GPT, of course, everyone knows this, and NLP, natural language processing, genetic algorithms, association rules, and of course, there are a lot more right there. So each AI category has its own application. For example, like what Dr. Liang has already introduced, the neural network can be used for the classification. For example, it can be used for the satellite or image object segmentation and detection. Okay, and it can also be used for some nonlinear regression, what I call the polynomial regression, for GIS data attribute analysis, especially the prediction. I will show the case about this later, okay? And then GPT, NLP is based on the language processing. They can be integrated in many GIS applications and boost the user interaction. And reinforcement learning, on the other hand, it can be used for GIS data geometry or spatial analysis. For example, it can solve the problems like the curve, arc calculations, the topology patterns recognition, something like that. And there are a lot more. For example, like nearby density clustering, that kinds of methods usually use in a global and local correlation calculation. And sometimes they can also be used in the raster calculation as well. So I would like to firstly talk about the GPT. Yeah, everyone knows GPT right now. It's a famous word all around the world. So GPT, the full name is the Generative Pre-trained Model. Okay, and in terms of when it comes to GIS, when it comes to the geospatial, how to use that, okay? So we don't really need to worry about or care about its public pre-trained model, because Microsoft, they spend lots of time, money, and resources, and has lots of algorithms to train these kinds of pre-trained model and make the product, the GPT. But when it comes to GIS, we don't really need to care about so complex schemas behind, okay? What we need to do is just to conduct the secondary training based on the existing GPT assistant or agent. And after that, we will need to extract the features from the secondarily trained model and then inject or integrate these kinds of features into our GIS system. No matter you are using, for example, the WebGIS like Experience Builder or Web App Builder, or you prefer the desktop application like AppProp or AppMap plugin, I mean, the GPT can be integrated into these types of GIS system. Okay, so let's take a look at a live example. Sec should be right here. So here is the example of GeoGPT. Okay, so I wrote this based on the Experience Builder as an example. So firstly, we will need to load the layers. Okay, so here we can see all train lines and the train station around the city, for example. Okay, so how do I use it? Okay, so I just type, for example, hi, please show me the metro on ground, which is active, maybe underground. Yeah, I don't know that metro they have a on ground train line or not. Yeah, maybe show underground. Yeah, okay. So I click the query. Okay, so just wait for a sec. It will give us the feedback of the metro train line from Chatswood to Rouse Hill. Okay, and then let's take a look at another example. I make this a little bit bigger. Okay, my screen might be a little bit small. So for example, thanks, and this time please show me the railway on ground and is operational, for example, and then we click query. So what we can see now, we got all train lines on ground, which is active, which is operational, okay, which is operational. And how about the train, but underground? Thanks. So we click on the query. So we just see that, I mean, some train lines around the city area, the CBD area, they are built underground, okay? So this time, please show me the, what's that, the light rail, for example, light rail on ground. And it should be active, okay? So let's click on the query. We can see the all light rails on ground, okay? So yeah, this is just an example to show how the GPT can interact with our GIS system. Okay, so GIS system, of course, it got the front end and the back end, and then GPT, when you need to use it, you need to integrate it inside the back end, and then use some schemas to communicate with your front end. Okay, that's types of GeoGPT, and there are lots of applications in addition to the train. For example, you can use it in property analysis and property, for example, property industry, for example, and you can also use it for other utilities and infrastructures, UI interactions. Okay, I mean there are lots of applications right there. So this is the GeoGPT case. Let's go back to our PPT. Okay, so the second one I would like to introduce is about a neural network. Yeah, so neural network, as what we can see in the previous presentation by Dr. Liang, it can be used for the object classification or satellite image segmentation and recognition. And on the other hand, it can also be used for the regression, and it can be used for our GIS vector data analysis. For example, your feature class, your shapefile, the neural network can help you to analysis and predict the values for the attributes. Okay, of course, the training data set and what I call the label, or some people call it the targeting attribute. Okay, they are neat as a training data set to train your neural network model, because neural network is a supervised training method. And in the real battle, many factors need to be considered. For example, how many numbers of the layers are there, and how many perceptrons in each layer, and the perceptron activation function, and the neural network area function, and the learning rate. Okay, and the optimizer algorithms, all of them are very important. And finally, they will determine how good your neural network is and how fast your neural network is. So why we say neural network is good in GIS data analysis? Because we all know that GIS data are quite sparse, okay? No matter from the spatial perspective or from the attributes perspective. And neural network is very good at dealing with the nonlinear polynomial regression. And these kinds of polynomial nonlinear regression are very efficient in the sparse GIS data. So we say that neural network is very suitable for analysis the GIS vector data. Okay. So here the factors that matter. We can see that, for example, this diagram, when we decide the neural network, you need to define, for example, how many layers are there and how many perceptrons in each layer. Okay. And of course, like the activation function is also quite important. For example, right here, the signals come in and then we'll multiply by the weights and add a bias right here in the perceptron, and then going into the activation function. There are heaps of activation function right there. I mean, there are a lot. And most commonly used will be sigmoid and red loop. I like them very much because it's easy enough and clear enough. Okay, but on the other hand, there are lots of these types of activation functions online, and you can search on Google. And when the signal comes out from the activation functions, it will go into the next iteration of the layers of perceptrons. So, for example, another factors like the logs functions, the optimizer algorithms, they are also quite important, and there are lots of options, right? I mean, now right here I just screenshot a few of them, but in fact there are lots of different options. And in practice, you will need to adjust your neural network by trying and find the most suitable one to your scenario and cases. Okay, so now I would like to show you an example about how to use the neural network for GIS analysis to predict the data value, predict the data value, okay? So what you can see the screenshot right here, we got the road network and we got the GNF dots. And then firstly, the purpose of this is to, for example, to predict the traffic volume based on the residential density and the road condition. Okay, so firstly, we will need to align the nearby GNF to the road segments, and then it will become stitched attribute called GNF total. Okay, it represents the residential density. And then we got another two attribute right here, the functional type or drive time, which means the road condition. Okay, and we can see the last attribute highlight. It's called AADT derive. I call it traffic volume. So basically, this is a training data set. We will need to find the relationships between the first three column, first three attribute, and the last targeting attribute. In order to do that, we need to have a polynomial non-linear regression. Please remember that this is not the linear regression. If it's linear regression, we don't have to use the neural network. Even in Excel, we can do that. But this is a non-linear polynomial regression. So we need to find out the relationship between these three attributes and the last targeting attributes. Okay, so I would like to show you in the real case how to do that. So this is the notebook in AWS, and I make this example quite long ago, actually. So firstly, of course, we will need to import the libraries. This is a Python based on the PyTorch and the NumPy, okay? So we will need to import the relevant libraries, of course. And firstly, we will need to read in the training data set into the Panda framework. So I have already turned the attributes from the feature class into the CSV, okay? And this can be done by lots of things like FME or ArcPy or other types of open source tool. You can do it. And then when you read this data, you turn it into the NumPy format, okay? This is like the outcome. We got the road condition, we got the residential density, and we got the targeting value, okay? And then the second step is to build our neural network, So in a class, I define the input layer and output layer. There are three input because there are three attributes and one targeting attribute, one targeting label attribute, okay? So we define the input layer and the output layer, and we define the hidden layer in between. So yeah, this is written in the class. We define these kinds of layers, the layers number, and we also define the activation function, like what I showed previously. I mean, we use the red loop function, which is easy, okay? And then after that, we finish define our neural network. And then we will need to pre-process our data. Usually, we will need to normalize the input data into the values between 0 to 1. So what you can see right here, the data are quite sparse, and some of them suddenly become quite big, okay? So we will need to normalize all of these data into the value between 0 to 1. Usually, we call it normalization professionally. Yeah, normalization, okay? So we need to normalize it, okay? So this is the output. And then we will need to set the neural network parameters, like what I showed in the PPT. And we will also need to set our loss function, optimizer functions, that kinds of things. So here you can see I use a most common loss function called MSE, okay, median square error. So this is the most common loss function, and I use the Adam algorithm as the optimizer, okay. And we also set the learning rate. And then we will need to turn this data into the tensor. Tensor is an important concept in machine learning, no matter use a PyTorch like what I'm using right now, or you use the, for example, the Google TensorFlow. I mean, you need to understand the concept of a tensor, okay? So, but anyway, because of the time, I just, I can't explain it right here. I mean, but you need to turn the data into the tensor, okay? And then after that, we can start to train the data set and display the intermediate values, okay? So for example, I set 2,000 steps and then with a loop, okay? And then we can run it and try and take a look. For example, try to run. At the beginning, we can see the error in the first step is very high. It's 70%. It's 70% error, and then it's gradually decreasing. Okay, you see the value is decreasing to only around 3.2%, and still decreasing and decreasing and decreasing. And then finally, after several steps, it will converge to a very low value, which is acceptable by your task or by your work. Okay, so now it's already dropped to 3.0% after 2,000 steps, after 1,900 steps, almost 2,000 steps. Okay, so we can see that the errors is dropping from 17% to only 3.04% at the end, which means that your neural network is getting more accurate. Okay, so when this value reach your reach your goal, for example, you said, oh, this error I can accept it, and then it can be used to predict our data. Okay, so this is the last step. Use the trained neural network model to predict the data. So we run it, it will be very fast to output the values. Okay, at the end, this is ADD derived prediction, and then okay, this is values we predict. So this is how we can use, for example, the neural network to help solve the attribute issues, to predict the attribute values for the GIS vector data like the feature class, shapefile, or even the GeoJSON can also do that. Yeah, depends on how you program it. Okay. So this is a real example of the neural network. And if you are interested about the details and I've made the video, you can scan this QR code. Yeah, I'm not sure you have enough time to scan it. Yeah, I stay here for 5 seconds and then I will go to the next slide. Okay, and then so for the next one, what I'm going to talk about is the reinforcement learning. So previously, we showed a case about how to use the neural network to predict the attribute value of the GIS data. So this time, we will need to use the reinforcement learning method to calculate the geospatial geometry, to solve the geospatial geometry issues. Okay. So reinforcement learning is a type of artificial intelligence where the machine learns by try and error. And unlike neural network, is not supervised, which means that we don't need to give it the training data set. I mean, we just need to set a goal and design our algorithms. And then after times of iterations and recursion, I mean, the reinforcement learning machine can reach our goal, can help us to solve the issues automatically. We don't need to train it. Okay, we don't need to train. This is the reinforcement learning. So this diagram simply show how it works. We define some algorithms and put it in the state. Okay, and then after the iterations, the parameters in the states are changed and adjust and optimized automatically. And after, for example, hundreds or thousands of iterations, the reinforcement learning machine will be adjusted to the most suitable settings to tackle our problem. So here is an example. Okay, so in this example, we can see that we have a long polyline which is broken into the vertices. The long polyline can always be represented by the vertexes. Okay, so it's firstly broken into the vertices. This can be done by third-party, for example, software like FME or even API can do that. And then here, for every curved section of a long segment, the RI needs to find out the circle that is the most approximate, that has the most approximate radiuses and centroids to represent. For example, this section of a curve, it can represent by this circle. with the center right here and the radius from here to here, okay? And then for this section of the polyline, this curved section of the polyline, it can be represented by this large circle with the radius from here to here and the centers right here, okay? And also, for example, for this one, even they are sparse, they can be represented by the circles centers right here, okay? And then the radius from here to here, okay? So this can be done by reinforcement learning. So after that, what it can be used? For example, we can use it to detect the sharp turning curve. We can use it to also find out whether it's a left turn or right turn. And it can also be used to find out, for example, the how to say that the distance between each curve. I mean, when we got the results from the previous diagram, I mean, we can simply search by the radiuses, and then we can detect the sharp turning curve, whether it's a left turn or right turn, for example, and then what is the specific radius for this curve, okay? So how to do that? Assume any curve can be represented by a part of a circle with a certain radiuses and the center position. We have the formula like this in Cartesian expression. This is the traditional ways of expression, and this is the polynomial form of expression. And then we will take several vertices together to establish the overdetermined equations as the reinforcement learning agent and states in order to discover the D, E, and F, which are unknown parameter. Okay, so once we determine the D, E, and F, we can calculate out the center of the circle, and we can also calculate out the radiuses of the circle by the square roots. Okay, but importantly, you just need to remember these kinds of things will be constructed as an algorithm and put in the state of Ri. So programmatically speaking, we need to turn the above formulas into the linear algebra, and then we have a lots of formulas in linear algebra to solve. For example, here we solve the x def by the least square solution. And then we inject these linear algebra algorithms into our Python code in our states as a Ri, the reinforcement learning state and status. And then after times of iteration or recursion, and then it will automatically find out the most suitable and most approximate solution. Okay, it will automatically find out. So we don't need to intervene it, or we don't need to give it any training data set. We just need to set up our algorithms, our mathematical solutions, and then we put it in the state, and then click running. After several iterations and recursion, the results will be found out automatically. So this is how good the RI is. It's usually, you can, of course, I mean, generally speaking, it's used in the robotic, but in GIS, it also got its application. In detail, I mean, this topic is quite complex, and I wrote the articles a quite long time ago about this, and you can find it on my LinkedIn, and it describes all the details and also include the full set of codes. I mean, if you feel it's useful for your work, you just take it, okay? So yeah, basically, I think, yeah, that's my presentation today. And about the neural network, you can also go to my YouTube channel, and I make some videos to talk about it very detailedly, because within a short time, I mean, lots of details are missed in my presentation. But if I'm interested, you can go to my channel, GIS Man, and then you can find out several videos talk about the neural network. Okay. So that's it, and thank you very much. I hand over back to Simon. Thank you.
Okay. Miles, could you stop sharing on this side? gonna jump in the Q&A. I think you didn't stop the sharing. Maybe I need to wait a second.
I think mouse you click to the pause sharing, not stop sharing.
Okay.
Yeah, stop sharing is at the top of the screen.
Okay.
Yeah.
Okay. Let's jump back. We have several questions from the audience. So let me move to Q&A. I think the first question is from the Bing side, and the Winston then they mentioned about it in the pipe example. We discussed about integration of domain knowledge. So what kind of form does it take?
Yeah, I can give you an example. For example, the in the pipe failure main prediction. So as consulted with the domain expert, they advise that the elevation difference is a key factor to the pipe failures. So we have the elevation data. This is from the public data sets, and we have the elevation information around the pipes. But what we need to do is to extract the information from this elevation data to create or calculate the like, for example, the ground level difference, and then to append this information or this calculation results to the individual pipes, and along with other features, so that in this way we can have this handcrafted features. So yeah, there are many other ways to incorporate domain knowledge, and this is one of them. So yeah, this is an example.
Okay.
Yeah.
Thanks for answering. So the next question they also mentioned about from the Riza injury, has there been proof of concept done for the predictive modeling on the water asset failure?
Yes, our center, Data Science Institute, has been working with more than 30 water utilities, and to test and validate our predictive modeling. And yeah, so yeah, that's all of this has been validated, and also we consistently collaborated with Sydney Water to test our modeling. So yeah, this are, I mean, yeah, the solution has already been validated.
Okay, thanks for answering, Bing. So the next question is about Miles, the GeoGPT. And Abraham mentioned about, so we are talking about the real-time data for GeoGPT, or it's like it's historical data for the data.
The data for the demo, I mean, is not the real-time data. The data, because it's just a chain line data. It can be found open source online. I mean, it's not the real-time data. But of course, it depends on how you use it. If in your application, like for example, you track the vehicles, for example, or you track other types of things, and then if it's real-time data, no matter by geo event or by MQTT, that kinds of the publisher. I mean, GeoGPT can also work for that. GeoGPT actually only act as the human and computer interaction media, yeah, from the GIS perspective. And of course, it will provide lots of conveniences. It will provide lots of conveniences when people query the features or query the geospatial data. So yeah, that's my question. That's my answer. Yeah.
Okay, great to have your answer. And for Annie's question, he mentioned about how do you know when your neural network is overfitting? And is there any step-tip cutoff point from my side? Yeah.
From my side or from Dr. Bin side, this one?
Your side, neural network.
Okay. Yeah, I can. Yeah. About this question, I can give my brief idea, and then I can also let Dr. Bin talk about his opinion. So actually, I mean, there are quite a few ways to see if the method, if your trained neural network model finally is overfitting. For example, you can compare the data of your for example, your prediction. Compare your data of your compare your data of a prediction in your test set, your test data set. Okay, and then if you see, I mean, for example, your current train result, the data is aligned with your prediction, but however, in another set of test data, for example, is tremendously offset from the target value attribute, and then this means that is overfitting. This is a quite straightforward way to detect in practice if your data is overfitting or not. It's just compare different types of test data set. This is my understanding. Yeah. I give a
Can I yeah, thank you, Miles. Yeah, I would like to add one more comment. So yeah, overfitting is a common issue in when you use machine learning. So usually we divide or separate the data set what you have into two parts. One is training data set, and the other part is validation data set. And for the test data sets, usually we call it test. That means that's for the production phase. We cannot see the test data set. So for the modeling phase, you have the training data set to train the model, and you have the validation data set to validate your results. So when we iterate the training procedure, so you can see with the iteration, the error or the performance, or we call the performance, or the performance will increase with the iteration, and you can compare this trend with your model on the validation data set. If you find that the curve changes the direction, or the performance decrease in the validation data set, that point is a kind of the cutoff. So you can stop the training. If you're still training, if you still keep training, you may find the training error or the performance on the training data set is still improving, but the performance on the validation test may become worse. So yeah, that's a point. You can stop training and to use the trained model for the testing or for the production.
Which means it's not converged anymore, even though we see the result is improving, but it's not converged. I mean, it's not converged in reality anymore.
Yeah.
Okay, thanks for our Miles and Bing's answering. So I'll move to the next question, and it's from the line. He asked, where did you see the Geo AI moving forward in terms of urban planning? So maybe I think both, if you're interested about urban planning, you can talk the main point between the Geo AI and urban planning, I think.
Yeah, Miles, you like to go first?
I first? Yeah, or you first? No problem.
Okay, yeah, that's fine. Yeah, I think well, one of the applications on top of my head is a change direction. So especially for the urban planning. So we can, because that's from the perspective of segmentation part. So we have the segmented of the areas of interest or the objects of interest, and we have the temporal satellite image data, so we can compare the difference of this segmented results and to see whether there are some changes in the trees or some changes in the buildings. So we can use this kind of information to support the urban planning or decision making.
Yeah, from my perspective, I can see it's not just moving forward. I mean, in the urban planning, I mean, it already happens in I mean, in the market. For example, some company like the Artistar and some company like for example, Good Location. For example, they all got these kinds of Geo AI and then BIM combining techniques to help their urban planning. They can predict whether this site is suitable to build and how high it should be, for example, and it can automatically detect whether it aligns with policies and something like that. And I can see that it had already been used more or less in the market at the moment. Yeah. So of course, moving forward, there will be a lot more. Yeah. No matter from the GPT perspective or from the prediction or correction perspective, the AI will play a very important role in GIS. Yeah, that's my idea. Thank you.
Yeah. Good to have your answers. So we have the final question from the band. And what from the water main failure prediction? So can the model be applied to the other company or region's water network to achieve the same result or not? So I think it's Bing's question. You need to answer. Yeah.
Yeah. The first one, actually, there are two questions in the first question. There's two sub questions. The first one, whether the model can be applied to other companies or regional water network. Yes, definitely. And the second one, whether we can achieve the same results. Yes. So both of the answers are yes. So yeah, because our center has collected the data set from more than 30 water utilities all over the world, and yeah, that's the largest data sets in of the water pipes in the world, and we have validated and tested our model on this large data set. And if you remember the curve I showed in the presentation, there's a range area, so that means that that's the lower performance and that's the low performance and the high performance, and you can see the variations of the curve. But within that range, we still that means that our model can achieve the similar results within this range. So yes, definitely for both yes for the first question. And second one, how long did it take for your model to be trained? That really depends on the data, how much data you have, and especially for the practical usage, usually modeling is not the time-consuming parts. The data cleaning and understanding is the time-consuming part. So because different companies or industry partners, they may have different data qualities. For example, whether the data is complete or not, whether there are some noise data or anomalies in data sets. So we need to validate and validate the data quality first, and then we can move on to the modeling part. And also, yeah, just keep in mind that this modeling is not just a one time, because every year you have the data, or you have the updated failure records. So this model is updated every once you have the data set. So this is ongoing modeling, not just the one time. So that means the model is updated, and also provides the consistent result, consistent modeling or prediction results.
Okay.
Yeah.
There's the other question from audience. From my side, I have another question about the climate change. I just want you can answer. My question is, can you discuss about how the AI and GIS are being used in address the climate change impact and improve the resilience of the urban infrastructure? Being on Mars can answer that. So what do you think about what kind of application or trends in the climate change and the resilience?
For example, yeah, maybe I answer first. For example, in the climate change, I mean, it's usually relevant to the remote sensing data. For example, the satellite data, the remote sensing data about the clouds, about the air condition, that kinds of things. I mean, so I think this is usually is a big data, and also the raster imagery data, and then GIS, yeah. Combined with AI has a lot of potentials in dealing with these kinds of, play an important role in these kinds of issues. For example, to make the prediction within the AI, I believe that it can have a better prediction. I mean, when the AI involves more and more, yeah, when the time comes by. And then also it can, the AI, because it's not just record and predict the reason, it can also accumulate the knowledge. The knowledge can be accumulated together, combining with big data warehouse, and then the system will be improved day by day. And then in that case, the prediction will be also be more and more accurate. Yeah, this is my opinion about that.
Yeah, from my end, I can think of an application of the carbon monitoring. So yeah, talking about yeah, speaking of the climate change, the carbon estimation is a challenge topic. So currently, the researchers have been using start to use the AI and machine learning and also remote sensing image data to estimate the carbon. So yeah, because previously the carbon storage is estimate or is measured by field sampling. So that's the time consuming and very expensive because they need to take the samples back to the lab and to do the measurements. So currently, there's some applications and research work being done to use to integrate the remote sensing data and to estimate the carbon. So I think there's another promising application, especially in the carbon monitoring and carbon change tracking.
So that's the great answer I can got, because my personal research interest is between the climate change and machine learning. So maybe I'm looking forward we have this kind of application in the future. And I think our webinar is ending. But if you guys still have a question, yeah.
The last question at the end,
Oh,
if you
okay.
go down.
Oh, okay. Sorry, just missed part of that. And I think the last question is about, could you give the example about application of GeoAI in the renewable energy? And knowing that this field is pretty new, less or no historical data available. So what do you guys think about renewable energy and application of GeoAI? Okay.
I'm just thinking. Marcy, would you like to go first?
Renewable energy, I mean, including, for example, wind, the solar energy, that kinds of things, and also include, I think, for example, the electric car, the EV. I mean, they can also be included in the renewable energy industry, I think. And of course, currently the data are not that much because this is an emerging industry. Yeah, but for example, something like the EV, the EV car, for example, that kinds of things. I mean, or hybrid, for example, hybrid energy vehicle, that kinds of issues. And then the data are becoming more and more nowadays. There are the checkable data. I mean, even the open source data to record the footprint of these kinds of, for example, the new energy vehicles. Okay, and so in this case, I think that. But of course, maybe I haven't answered this question because, yeah, the condition of this question is with less or no historical data available. So, yeah, maybe I haven't really answered this question, but because no matter GIS or AI, it really depends on data. I mean, without the data, any software or any algorithm is just like a vessel without the water. So it must have some data as a foundation. This is what I'm thinking. Maybe I haven't really answered this question. Sorry for that. Yeah.
Yeah, speaking of the limitation of the historical data, I think one of the techniques could be useful here is the transfer learning. Transfer learning is kind of machine learning technique which train or model on one scenario and can be applied or extended to another scenario. So this technique could be helpful. Yep.
Okay. So we got another question from the pen. So if you guys can are willing to answer. So I think it's more for Bing's side. Regarding the water main failure prediction model, is it currently only using for research purpose, or has it already commercialized, like as a SaaS product? And I can see it being useful for a utility company. And what should they do if they are interested to using your model? So what kind of comments you have for Ben's question? Yeah.
Yeah, currently, the model is being operationalized, and it's being used by City Water. And also, if you what do you mean? What is the interested? What should they do if they are interested in using my model? So yeah, just contact me or contact our center, and I can provide more details about the modeling of this for this water mine failure prediction. And yeah, do you want to go to the next one?
Okay, so to the last one. Okay. What kind of opportunities would you use the IoT devices with AI?
From my perspective, I think there are two types of usage. IoT, you can use it. IoT device, you can use it as a receiver to censor the environment data. For example, it can use to sense the air condition. It can use to sense, for example, the humidity. Data in the air, and then when connect these kinds of data, the AI can process it, and then with a learning model, it can predict the stuffs. And this is one usage as the receiver IoT. Yeah. Another one, for example, IoT device, it can also be used as a media. For example, some IoT device with vision function like the CCTV. I mean, CCTV is, of course, is not the IoT, but some wireless, for example, some wireless IoT can be deployed in the field. For example, the farm or the mining site. That kinds of things also got different types of, for example, like the vision sensor, that kinds of thing, like the camera. And then you can combine the computer vision. You can combine the computer vision to detect the objects. For example, when the bird, for example, for the environment protectors, I mean, they can deploy the IoT with a camera, for example, wirelessly. I mean, on some places. And then, of course, you need to solve a power issue, right? I mean, and then after that, I mean, it can detect the objects. You can use a computer vision to detect the objects, the animals, or that kinds of things. And then this is one of the application of IoT. When it detects it, you can count the number. For example, how many birds flies by and how many insects or how many animals of certain species go by. And then you can use a computer vision to detect it and collect the data. This is what I can think in my mind. Yeah. About IoT, yeah, with AI.
Yeah, a quick answer from my end. The first is IoT can be used as a data provider. You know, it's like it's kind of data sources which can provide the real time data. And the second one is the integration of AI capabilities into the IoT devices. So currently, I think most of the applications of the IoT is IoT provider data and the machine learning model or AI model is on the cloud. So it's like a centralized application or solution. And in the future, I think not in the future, currently it's happening now. So people are integrating the AI capabilities into the IoT device, which is called Edge AI. So this is another opportunity in this area.
Okay, because so many diverse answers and questions, I'm very happy to have this kind of session. We're gonna have a series, the AI's webinar later, but we are still planning. And if you guys join this webinar later, we still can watch on the recording. And also you can reach out to our presenters, Miles and Bing, to discuss some specific questions on your side. So I'm gonna say we are ending right now. So yeah, hopefully we can see the next time, and we will talk about some different technology and different topic. Okay. So see you guys, and we'll keep our eyes for the website for the recording, so you can review our video and to figure out what I'm going to talking about in this presentation from Miles and Bing. Okay. See you.
Thank you.
Thank you.
Thank you all.
Thanks everyone. Bye bye.
See you. Bye bye. Thank you very much.